welcome back. Hope I didn't leave you in too much suspense after that cliffhanger. So now we are finally going to be able to solve what the mystery of x, y, and z is. So by doing that, we are going to harness once again the magical power of matrices and introduce a new friend of ours, row echelon form. So row echelon form, or REF for short, is a way to describe a matrix with these three properties. So our first property is all rows of all zeros are at the bottom. So if by chance we had gotten a matrix that has all zeros, then that would be whoop, pop to the bottom. Our second one is each pivot is equal to 1. So wait, hold up. What's a pivot? A pivot is the first non-zero entry of a row. So for example, this is our pivot value of the first row, which is 5, 2 for the second row, and 3 for the third row. We want each of those to be equal to 1. So luckily here we see our pivot is equal to 1 in our first row. And then for our third condition, we want each pivot to be further to the right than the row above, or the pivot in the row above. So you'll see here, this is where we left off, and you'll see the pivot in the second row is 5, and it is right underneath the pivot in row 1. So we need to move that in order for this to be an REF. So let's get started. So first we want to get the pivot in the second row to be farther to the right than row 1. So what we can do is we can multiply row 1 by -5 and add it to row 2 and then store that back in row 2. So let's do just that. We're going to do it right on over here so we don't run out of space. And if you notice that we're not doing anything to row 1 or row 3, so we're just going to go ahead and copy those back on in here. And then we are doing something to row 2. We're changing what's stored in there as told by our arrow. So we're going to be taking -5 times row 1 and adding it to row 2. So -5 times 1, which is right here, and adding it to 5 is going to give us a 0. Which is exactly what we wanted, so we're on track. -5 times 1 plus 3, that's going to give us a, what is it? Oh, -2, perfect. And then our -5 plus 2 is going to give us a -3. And then our -5 times 0 plus -4 is going to give us a -4. Okay. So now what we're going to want to do is we're going to want to make sure that our pivot, which is currently right now in our second row, is -2. We want that to be equal to 1. So we would have to multiply this whole row by -1/2. However, we want to avoid fractions as much as possible just because it makes our lives a little bit easier. So what we can do is we can do a little switcheroony with rows 2 and 3 to get this -1 into the second row so we don't have to divide by anything. So let's just go ahead and do that. Okay, so now we want to get our pivot equal to 1. So how we can do that is we can multiply all of row 2 by -1 and then store it back in row 2. Just like that. Now once again, we are not doing anything to our first or our third row, so we can just go ahead and copy those back on in there with no issue. However, we are switching all of the signs on our second row, so let's go ahead and copy that on in here. Perfect. So now we have successfully put our pivot equal to 1 in our second row. But now we need the pivot in the third row to be farther to the right than the one in the second row. So how we can do this is we need to get this to equal to 0. So what we can do is we can do 2 times row 2 and add that to row 3 and then store that back on in there at row 3. So doing this will give us our 0 right there. So then we will have, once again, not changing anything about the first 2 rows. And then we're taking 2 times row 2 and adding it to row 3. So 0 times 2 plus 0 is still 0. 2 times 1 plus negative 2 is 0. 2 times 2 is 4, plus negative 3 is going to give us a 1. And then our negative 1 times 2 plus negative 4 is going to give us a negative 6. So now let's double check. Are we in REF? Do we have all rows of zeros at the bottom? Yes, we do, because there are no rows of zeros. Do we have each pivot equal to 1? Check. Do we have each pivot further to the right than the pivot above? This pivot is further to the right than this pivot. This pivot is further to the right than this one. So yes. So now we are in REF. Okay, so now how can we use REF to solve the mystery as to what x, y, and z are? The answer to that question is back substitution. So remember that this is representing our coefficients. So this is our A, and this was our B, and we've just manipulated them, switched them around a little bit. They still represent the same kind of data. So we can take this A matrix here and then bring back our x, y, z vector, and then set that equal to our B that we had just manipulated into this. So we have 0, negative 1, and negative 6. Okay, from there we can do a little bit of matrix multiplication and get our linear system of equations once more. So we're going to have x plus y plus z equals 0. We're going to have y plus 2z equal to negative 1. And then finally, we're going to have z equals negative 6. Now, back substitution implies we're going to do some substitution. So we can plug this value of z right on in here for z. So then, when we do that, we're going to have y plus 2 times what's z? Oh, Bonnie should ask. Negative 6. And that is going to be equal to negative 1. So that means we have y minus 12 equals negative 1, and y equals 11. So now, all we have left to solve for is x. And luckily we know what y and z are, so we can just substitute those ones on in here. So we're going to bring it all the way on over here. So now we have x plus, oh, what's y equal to? 11. And then plus z, what's z equal to? Negative 6. And that is going to be equal to 0. So now, solving this, we have x plus 5 equals 0, and we see x is equal to negative 5. So now we have finally solved the mystery as to what x, y, and z are, and we know that our final solution is negative 5, 11, negative 6. There we go. So now if you don't believe me, you can go back and check your work by plugging this value of x in for x in each of these equations, 11 in for y in each of those equations, and negative 6 in for z in each of the equations. And then if it all checks out, that means that we have successfully used row operations and row echelon form in order to solve this linear system of equations. So I'll catch you next time.